Okay, so welcome to this week's Origins Colloquium. It's a pleasure to introduce Duo Zhu, who has been for the last almost 3 years an Origins Fellow at the University of Virginia in the astronomy department. He came to Virginia from a stellar Optimus group. I guess your PhD is from University of Texas, is
Texas,
it, Duo?
Yes, Texas, Austin.
Yes, and then has been working then both in his PhD thesis and also in his postdoctoral position in various aspects of machine learning that I think we'll hear about today. And soon we'll be moving to CETA at the University of Toronto in a joint CETA fellowship, but also special machine learning and postdoctoral fellowship. So please go ahead, Duo.
Thank you. Thanks for the nice introduction. So today I will introduce our...
Maybe just turn on your local video on so we can see you more clearly.
Okay. Great.
Yeah.
So I will introduce our work and also some overview on our machine learning methods and application to astronomy studies, especially in the field of star formation and its medium. So I want to advertise our homepage here that's gallery our all AI application in ISM and star formation studies. So to give a really brief overview on why we care about star formation and its medium, they are the most important component in our galaxy because they regulate the evolution of our galaxy, such as from the atomic gas from H1 to undergoing chemical evolution to form H2, where that's the birthplace of stars. And then the molecular cloud will undergo with the gravity, turbulence, and magnetic fields. They will form a variety of structures such as cores, clumps, filaments, and that's the precursor of star formation. And during this stage of star formation, the stars, the young stars, will not only accrete gas, they are also returning gas to the surroundings. That's called feedback. So this feedback mechanism will inject energy, momentum, and also hot gas into their surroundings to support the cloud or even destroy the cloud. Once the star is formed, they will undergoing nuclear synthesis and then might be a supernova or planetary nebula, also returning ionized gas into the surrounding ISM. This is also metal enrichment. So all this cycle will undergo times over times, and then that's the evolution of our galaxy. When we study star formation and also ISM, we have tons of data. So we are not able to examine that one by one. So that's the main reason why we use machine learning or artificial intelligence to help us. And also, there is one advantage for machine learning, that is they can deal with high-dimensional data. Since for human, we usually do images. Even for cubes, it's really difficult for us to fully inspect or examine them carefully. So that's why when we have full-dimensional data, such as position, velocity, including spectral information, machine learning can help us to segmentation or do the inference. And another powerful part of machine learning or artificial intelligence is they can learn the representation or the embedding information of our data set. So in that case, the machine can bridge between the simulation where we know the physics to the actual observation. That's our observables. So we will list some of the examples we did in our work to use artificial intelligence to bridge between simulations and observations. For machine learning 101, so usually we have two different categories of machine learning. That's one is supervised, the other is unsupervised. And unsupervised means we do not have to provide any labels or masks, or we do not have to provide any prior to the machine learning model or the algorithm. The machine will just conduct themselves to do their task, such as clustering or dimension reduction. I will talk about all this later in my review. And for the supervised learning, that means we need to provide them the model or the algorithm proper labels or masks or the prior knowledge to let the machine or the model to do exactly what they want to do, what we want them to do. So that's the supervised learning. So we will provide some prior knowledge to the model. So for example, the unsupervised learning, one major task in astronomy is clustering. So usually we have tons of data, and without some human prior knowledge, we just have the machine to do some cluster, such as we have Gaia astrometry data, we have proper motion, we have distance, and then we just let the machine, the unsupervised learning, the DB scan, to clustering the stars into different groups or clusters. So they may belong to different star clusters or different molecular cloud, such as here, the machine just automatically group the stars into different categories. Another topic is to reduce the complexity of our data. That is dimensionality reduction. For example, we have spectral data that has multiple channels, hundreds of channels, and we want to see the similarity between different spectra. So one strategy is using T-SNE map, that's a reduction, dimension reduction method, to map all the high dimensional data onto a two-dimensional space. And we can know the similarity between spectrals, such as here, there are spectral coming from bubbles or coming from outflows, or even just the rest frame molecular cloud, that's a Gaussian-like spectra. Another interesting topic that's in that time domain astronomy, that is anomaly detection. For example, when we have light curves, and we can let the machine to identify or to detect some anomaly, such as they are not typical to supernova or other typical physical process or physical event. So this anomaly detection can help us to identify some of the unknown physics or unknown event. So that's really powerful for some of the survey data, for example, from LSST. And for the representation learning, that's the most important part for machine learning, because that's the only thing machine can do, but a human cannot, because we are not able to extract all the information from our data set, but the machine can do that. For example, here, machine can extract the similarity between galaxies, and they can know how similarity between galaxies based on the representation or the embedded information. For example, here, the elliptic galaxy or the spiral galaxy, and they even have a different viewing angle can be separated on this representation for the lower dimensional data space.
I have a quick question. You went to clustering and DB scan. I'm trying to remember, is DB scan a machine learning method, or is just running an algorithm to find clusters?
Generally, it's a machine learning method. It's not deep learning, it's a machine learning. Even though, and also random forest, and also k-means, we all usually call that machine learning, but not deep learning. It's also machine learning, it's machine learning, usually we call that. It's really general.
But it learns, does the clustering algorithm improve itself or something, or it's just running an algorithm?
They have some parameters you can set, such as the distance between clusters. You can set some numbers or some criteria to get what you want, such as you can have, for k-means, for example, you can define the number of clusters you want. For example, you can have 2 clusters, class 1, class 2, or you can have different inner stage, and depends on, there are some hyperparameter you can use when you tune or let the machine to better to clustering on your need or on your requirement.
Okay.
Yeah, and another topic is the supervised learning. That's what astronomers were really interested about, because they are doing what we want them to do. For example, classification is is really different from clustering, because classification, that means we need to provide a label for the machine or for the algorithm. For example, here we have multi-band observation of the near infrared of the star, and we want to classify them to be class 1 or class 2. And then the machine can do a really good job, and with minor some misclassification or false positive. And another huge topic in astronomy, that's regression or the fitting. That's always what we do. For the spectral fitting, that's straightforward, that's one-dimensional. But for image, that's difficult. So that's why machine can extract some information from the images and then do the regression or the fitting in a smart way. For example, we have outflow images, and then we can let the machine to learn how that look like and what's the embedded information to infer the young star mass or the inclination angle of the outflow or the position angle of the outflow. All these methods are usually just adopt a simple neural network that's with some max pooling layer, with convolution layer, or activation layer. And at the end, there is an embedding feature vector, and the machine will just extract this information from this embedding feature vector to do the prediction, such as classification or regression. And another more sophisticated task is segmentation. So that usually relies on the pixel level mask. So that's why it's a little bit different for the architecture. So here we have a more improved UNet architecture adopted in this task. For the segmentation, the usual way is we give the model the data, the image or the data cube, and the output will be exactly the same dimension or the shape of the data. So with the mask on whether the object is being segmented. So they have two parts, the encoder and decoder. The encoder that will break the input data into feature vector or the embedding space, and the decoder will translate all this embedding information into our target, such as the segmentation result. And there is another hot topic that's transfer learning, because there are a bunch of models being trained on the neutral image or the natural image on our daily life, such as animals or other daily objects. And we can just adopt that machine learning model and retrain that on a subset or limited number of data sets we are interested, such as galaxy merger system. And the machine learning model can just identify all this galaxy merger system based on a little bit or light-weighted training. So that's really time efficient and really save our computational resources. Another huge topic in machine learning, that's the generative model. So there are a bunch of generative model. You may know ChatGPT, that's text generation, and DALL-E is the image generation. And there's also Sora, that's the video generation, and MuseNet, that's the audio or music generation. And the main difference between generative model and the discriminative model that's similar to segmentation or the regression, that requires us to get the conditional probability. So that's given some observables. And based on that, we predict the physical quantity. So that's the conditional probability. But generative model will learn the joint, the entire space distribution, data distribution. So that can generate new things without even giving any prior knowledge or prompts. So there are a bunch of applications of generative models in astronomy. The really straightforward one is generate new things, such as we can generate galaxies based on some scratch, such as we can draw some artificial morphology, and then the machine will generate all similar what the galaxy look like. That's all similar to what DAISY or other sky survey data look like. And another powerful part is the denoising or removing the RFI, that's the inference in radio astronomy. The GANs, that's the generative model, can generate the actual signal by removing all the RFIs from the actual observation. And also deblending, that's we have observations that have the overlay on the outside of different galaxies at different distances, and the machine can just disentangle all this stuff and deblending all these overlapped galaxies. And this is also powerful in the sky survey data. So here are some of my thoughts on why we use machine learning and how we use that. So the basic idea or the fundamental of machine learning, that's learning the representation or the data distribution. Since once we learn how data look like, then the machine can just do their task, such as segmentation or regression, based on the embedding information or the knowledge. And for image, especially in computer vision, we have kind of the common sense that image data is really redundant. So even with a part of or subsample of the information from the image, we can reconstruct the entire domain or entire space. For example, here, even we have lost 75% of the information of the image, we are still able to recover most of the details in the image. So that's really powerful when we do the clean process, such as from interferometry observation, where we only sample a part of the forest space or the UV plane on the sky. And here are some results has been applied using AI to do the clean process on interferometry data. Here's the dirty image and the AI and also AI prediction and also the ground truth. That's the real sky image. And we can see if we do the use the clean process, they are not that good, but we can still see we can recover some of the bright dots or bright blobs, but some structure is missing in the clean process. But machine learning can recover all this stuff. So that's really powerful when we apply machine learning to this kind of task, to dealing with the missing information or some limited subsample information. Then I will just introduce our endeavor or our hard work using machine learning to study star formation and intermediate. So I will starting with some simple case and then step by step to the more sophisticated models. So we're starting with a really simple case, such as using random forest. It's a machine learning method, not deep learning. So do some classification to identify or classify the bubbles from dust emission. So random forest is based on decision tree. So they have different criteria to separate different categories or classification or different classes in the object. And in our case, we use random forest to train on both synthetic observation and also real observation. The reason why we include synthetic observation, that is, in the real training data from observation, we have bias. The people all usually just identify really bright sources or bright bubbles are missing, and they are missing some faint, the B-type star-driven bubbles, that's all more like yellow or fainter bubbles. And we use synthetic observation to complementary or to supplementary this missing category in the training set. And the result is, after we train the model, we are able to identify more real yellow bubbles that's driven by B-type stars. So this gives us confidence that synthetic observation is have great potential to help us to deal with the imbalance in training set and help us to deal with the machine learning training, especially applied to observational data. And this is really straightforward, just to know is bubble or not. Then we want to have a pixel level segmentation of bubbles or feedback features, such as outflows. So we use UNet. As I mentioned before, this is just encoder and decoder. We are able to get pixel level prediction or mask on the location of feedback feature or our target. And further on, we can use machine learning to do the regression or inference. For example, here, we are using machine learning to infer the actual mass associated with feedback by excluding all the contamination on the line of sight, including foreground or background or the rest frame velocity that are not associated with feedback, but they are just from the domain cloud or the host cloud. And the machine can extract this feedback emission clearly and accurately compared to the other method, because usually we are overestimate the mass or energy coming from bubbles because they have contamination from foreground or background. A machine can do that really good. This is one-to-one line, and machine can do perfect job to do the regression. And with some...
Maybe I could ask you just one quick question, sorry. I know we'll have a discussion later as well, but surely it's only as good as the model it's trained on. So do these methods involve?
That's true, that's true. So the base idea is we train the model that's to our knowledge, that's the ground truth. But in reality, we cannot do the perfect simulation or perfect ground truth because we are always missing some of the physical quantity or physical mechanism or physical processes. But as to our knowledge, or there's order or approximation, they are as to our knowledge. That can be a good approximation to infer or to estimate the physical quantities. Definitely, that depends on how we train the model and the model or the simulation data, whether they are valid or whether they are good enough to represent the real world. Definitely, that's always the case or always the challenging part for machine learning. We want to make sure our knowledge or the synthetic observation can be close or to be similar to the real data as much as possible. That's a good question. So that's
So what happens?
challenging
What would
part.
happen if the model was terrible? It would try and do something.
That's good point. If the model is not good, then why do we run this model? They cannot represent the typical world. They cannot represent the physical or the astronomy phenomenon or the astronomy condition. So that's not good for our machine learning perspective, but that might be just the zeroth order approximation. So that's why we use simulation and synthetic operation, but not analytical models for our training. So that's a good point.
Well, maybe we can come back to that later. Yeah. Okay, please go on.
I can ask one other quick clarifying question. So you're not identifying new B stars or embedded B stars in the
No,
just new bubbles.
Just bubbles, just
caused by
structures.
their feedback.
Yeah, the structures.
Thanks.
Well, identifying stars, that's point source extraction. So much easier for us. We are doing the morphology more.
Okay,
Yeah.
thank you.
But that's the preprint or the tracer can trace some of the B stars. If you have identifying bubbles, you can identify without any driving source in the center.
Okay.
Sure. With all this prediction, we can do further analysis. So that's what our astronomers do, such as we can calculate the power spectra of the feedback region and compare that with the usual region, the common region. We can see the feedback region might have some energy injection scale, such as similar to the outflow typical length or width. Yeah. And another strategy, another application that is using this complete sample derived from machine learning prediction. We have outflow sample, and then we can compare the outflow orientation to the magnetic field's direction. And we see there are some alignment, but not misalignment between B field direction versus the outflow orientation. And also we can do further inference, such as we can infer the outflow properties based on outflow observation, such as the multi-channel CO emission, molecular line emission. So we can infer their mass, inclination angle, and also the position angle. And we also do some control test. We exclude certain mass or inclination angle or position angle out of the training. So they will never see this parameter before. And the model can still do smartly to do the interpolation or to explore the parameter space and get some reasonable result. So that gives us confidence that machine, they are doing some reasonable job to do the regression or do the inference. Another inference work that's predict the magnetic field strength direction here based on the morphology of gas. This is inspired by the observational evidence and also the simulation theory that magnetic fields can regulate the motion and also the morphology of gas, both in atomic gas and also molecular gas. Since in simulation, when there is magnetic fields, the velocity dispersion perpendicular to the magnetic fields will be smaller compared to that parallel to the magnetic fields. So that's why we can predict their strength, their direction based on the morphology of gas. And our prediction is consistent, highly consistent with the Planck observation. So that's also a great demonstration of the validation of our training set, of our machine learning model. Then I will just talk about how we apply the generative model to our astronomy task. Since usually we thought generative model is just generating new things, not doing the prediction or just doing inference. But I want to say, since generative model can learn the joint probability, they have the potential to learn the actual embedding or the representation of the data set and to do the proper prediction based on our certain condition or the input. So for example, we can give them observables such as the column density or the other emission data, and we want the certain or the one-to-one mapping of our output or target. So a brief introduction of generative model. There are three widely used. There are more, but these three are widely used. The variation autoencoder, and again, that's the generative universal network, and also diffusion model. And they have both pros and cons. So for astronomers, we just care about high quality and their model convergence. We don't care about speed because we can train for a longer time. So we just choose diffusion model in our study here. A more detailed introduction on diffusion model. So this diffusion model is based on the Markov chain. So it's really natural to get the proper image or a certain image really backward to a random noise image. That's by adding all the random numbers or random perturbation on this image. And this is straightforward. This is a Markov step. And the model will do is to recover from the noisy stuff to a real or the true clean image. So this is what diffusion model will model in their Markov chain. So in this case, we are using the conditional diffusion model. So that means we want the model to do exactly what we want, given some condition or the input, and generates the specific output that resemble our input. For example, here, we use diffusion model to predict the number density based on the column density observation or the extinction map. So the extinction map is really easy to derive from the dust extinction or the molecular line emission. But the number density is a key quantity that regulates all physical processes in astronomy. And we have diffusion model prediction, and we have some other power law conversion, simple astronomer like the power law or linear conversion between column density and number density. We can say diffusion model has a smallest dispersion and highest accuracy. And we also test our model on real data that's in torus filaments. And our prediction is highly consistent with the previous estimation using other tracers, density tracers, such as C3N. That's really convincing and also promising for us. The machine is doing a reasonable job to predict the number density in molecular cloud. And another topic is using diffusion model to infer the radiation field, because this is also a quantity that's really difficult to measure. And we're starting with 3 bands emission, including short wavelengths 4.5 micron and middle wavelength that's 24 micron. That's from warm or relatively colder dust from space observation, and 250, that's cold dust from Herschel, to infer the actual radiation field. And we also do some tests on the test set that's not including our training, and also we generate new test set that's using new dust models. And we also change our physical condition and run new simulations and to test our model performance. When we raise the radiation field by a factor of 100, the model still okay to do the prediction, although there are some systematic offset because we only train the model on a fiducial value of 4 G naught, roughly 4 G naught here. But the model is able to extend their capability to infer a wider parameter space. So that's the powerful part of generative model than the discriminative model, such as the usual UNet or convolutional neural network. And besides the prediction, I also want to highlight the diffusion model or generative model can also do some of the segmentation tasks, such as segmenting specific filamentary structure. This is this filamentary structure might caused by the collision of 2 clouds with reversed B fields, because they have specific features, such as they have spike across the filaments, perpendicular to the filaments. They have some fine features, not similar to a cylindrical or the Palmer profile filaments. So this method can give us some sample or the candidate on the whole sky to give us further sample for us to do analysis, whether these filaments are formed by collision or there are other forming mechanism of these filaments. So this is also a segmentation task that generative model can do. And there are also ongoing work I want to highlight, such as we are using diffusion model to predict the B field strengths, because B field strengths, that's a really big topic in the field of astronomy. It's really difficult to predict. So we adopt diffusion model to infer the B field strengths based on certain input, such as we train our model to predict the B field strength, but only on column density or with additional B field angle, since that can be derived simply from polarization from dust observation, such as from Planck or from GSMT, GSMT, or other sub-millimeter observation. And then we're also adding one more piece of information, that's left side velocity dispersion as well, to compare different model performance. As here, we can see they are doing really good job to predict a wide range of magnetic field strength. And I want to highlight that the DCF, the generally used method to calculate the B field strength, all take this three piece of information. And there's another straightforward way, that's using Quadrat's law, that is convert from density to B field strength, but they have larger dispersion, as seen here. And to convince why we use 3 channel, not 1 channel, we do some evaluation. We only train the model on specific type of kinematics, such as cloud collision scenario, and exclude all the non-collision case in our training. And we test that on the totally new simulation that's really new because they have different dynamic, they have different structure or physical processes happening here. And when we have 1 channel that's only with common density, they have larger dispersion compared to the power law, definitely. It's a similar dispersion, but when we add in one more piece of information, such as the B field direction, the dispersion shrink, and we're adding more, such as the velocity dispersion, we have much better prediction. Here is the relative error. We can see there is a long tail or underestimation of the B field strength in the power law conversion. But the machine learning, they might have some systematically overestimating, but generally the dispersion looks much better than the others. And besides the test on the Enzo simulation, we also test on a totally new different code running different physical condition. We are running that using Orion with a turbulent box and with a periodical boundary condition and assuming isothermal. So that's really different in our training set. So if we compare with the previous trained power law conversion to our DDPM, we can see they have totally different data distribution. So that's why we argue the diffusion model is really good at exploring the new power space. So even this data is never seen before, they are able to do that. So that's why it's really good strategy to apply DDPM to the actual observation, because in observation, this is new data that's the model has never seen before. Then I want to also highlight some potential application of DDPM can do, such as they can generate new things, the turbulence. Since running turbulent box might take a while, but generating a turbulent patterns from diffusion model just takes seconds. And they can generate the same in the power spectral and also density PDF. So that will greatly enhance the speed in our generation of the turbulence patterns. And I also want to just introduce or highlight some of the potential future perspective in the diffusion or in the machine learning perspective. There is always a debate that foundation model might be the next generation of our machine learning approach or machine learning community, because foundation model, they will learn everything they know from our daily life. And with this foundation model, we can do segmentation really good, such as the Facebook, they just published they published this a while ago, 2 years ago, segmenting everything model. So without proper training or fine tuning, I just load this JWST data on the website and let the machine to just segment all these galaxies, and they can do a really good job. And I can also give them some prompts, such as I tell them this green dots, this is galaxy, and some red dots, the pink dots, that's not galaxy, or the background we want to extract. They can do much better to identify these faint galaxies as well. So we can all use this machine learning technique for our astronomy tasks, and they can give you better than expected, especially when you use the threshold cut or even simple method to do the source extraction or segmentation. And another potential trend is the multimodality learning or the multimodal learning. Since in astronomy, we have different type of data. We have image data, we have spectral data, we also have multi-wavelength, and we also have multi-messengers, such as from neutrinos or gravitational wave data. We also have the tableized data, such as Gaia. We have motion, we have distances, we have photometry numbers. And then all the data can be combined together to have a more comprehensive model to conduct better inference or prediction on the physical quantities of our object, such as here to predict the star's property, temperature, surface gravity, and also here, they combine all different type of data, including gravitational wave data, to do the prediction. So all this can be the future perspective for the astronomy. So to the end, I just want to highlight that AI is evolving really fast. So you can try as many models as you want, and just to make sure you will train the model properly and also always examine your data at the end of the machine learning prediction, because machine might sometimes fake you or just force you to fool you on some of the prediction, just to make sure you use the data from machine learning with cautious. So I will stop here and take any questions. Thank you.
Thank you very much. Great, so we can transition to a discussion and questions now. So are there specific questions about the duo?
Can I ask one in here, Jonathan?
Yeah, please go ahead.
So about the cleaning algorithm, I know it's not your specific project, but I know like a big factor that ends up causing a lot of differences in the quality of the final images, or like choices that we make when cleaning.
Exactly.
Weighting, how deep we go, whether we're over cleaning.
Yes.
So is the AI approach just kind of like, you think that just kind of gets rid of all the human biases, or is it like a completely different routine instead of even running T-clean? Like, you know what I mean?
Yeah, that's a good point. So that's the short answer is AI cannot do exactly to recover the ground truth, exactly the ground truth.
Right.
They will also have some uncertainty. That's the short answer. So for a more explicit, to be more elaborate on that. So for example, for the DDPM, they have the random noise to be starting with to recover our ground truth for our image. The random seed can be changed.
Right.
And we can also have a parameter called beta, the chaotic or the uncertainty during our, or the stochastic, how stochastic in our process is. So we can make them to be a deterministic process, or we have some noise being introduced during our recovery to better capture the main feature but exclude any artifacts. So there is some uncertainty, but from our test is, even we tune the beta and change the random seed from the starting point, the convergence is really good. They have small dispersion, but they have dispersion. So we would say maybe they can have less variation or diversity compared to human.
So like the artifacts, that's the ADA feature. And
they can introduce.
Right. And that's okay.
Yeah, that's similar to how we choose the threshold when we do the cleaning.
Right.
Exactly that.
Right.
Yeah, and also for cleaning, that's the main challenge for the cleaning process is we cannot do really large map. The bottleneck here is, I thought 512 is already 512 times 512 image is the upper limit for the current DDPM image.
Right.
So to have larger map, they require larger GPU or better computing resources. But that's not possible for our scientific research. That's all in the industry. That's too expensive for us.
Thanks.
So there are some trade-offs here.
Yeah, yeah.
Let me ask a related question about the quantifying the uncertainties in the machine learning prediction. I mean, you mentioned we can just do an empirical direct measure of the dispersion from our model, testing on unseen data, but there are systematic uncertainties. You mentioned earlier about how good the model is and so on. Can you comment about, in general, how easy it is to assess the uncertainty in the prediction?
That's a good point. So for the intrinsic dispersion, that can be quantified much easier because we can tune some parameters and we can have different prediction or inference. But for the systematic offset, that's difficult because, as I have shown before, such as for infer the magnetic field strength, or the number density or the radiation field. If the real world, they have systematically totally different distribution, data distribution, such as they have different intensity, different photometry compared to our training set, then the model may give you some systemically offset prediction because the model have never seen that before. So that's why, to our knowledge, to our best, we should include as many possible scenarios as possible to let the model to learn the all possible scenario. Although the real world, they might have part of the out of distribution, but they're still really nearby. So that means in a Gaussian distribution, they are located at the 3 sigma or even 2 sigma of the Gaussian blob. They are not far away, all the way, such as 5 sigma or 6 sigma away from the main distribution of our data set. Then that should be okay. If we have some ancillary data for examination, such as if we predict the magnetic field strength on the whole sky or on the Mercury cloud, we can have some independent check, such as from Zeeman or from other method as an ancillary check to know whether the machine is doing the reasonable job or they have a systematic offset. So that's what we can do from our best, because we always do not know the ground truth. That's the main challenging part for our astronomy studies.
Mm-hmm. Okay. Other questions for Duo? We have a lot of applications, at least in my group, for looking at stars now, young stars, trying to find stars. You showed this, one of the last slides, finding structures in general. I think you showed a map of James Webb galaxies. You know, the problem we have, say, in James Webb images of very nebulous regions is finding stars to some level. So perhaps, I don't know if you want to comment on source finding methods here.
Right, source finding, that's similar to the segmentation task. So there are a variety of the segmentation method we can try. So I would say there is no perfect one. So we always have to compare with different models and also check their performance and to choose the one that close to your expectation or your requirement. Because different people, even among the astronomy community, different people may have different opinion on the source extraction, such as they might regarding this source is after the stars or the artifacts is not, or they are galaxies, since there are other methods that can be distinguished, but from a single image, there are some arbitrary among different opinions across different people. So to be short, we still need to evaluate by human, definitely, always. So there is no perfect tool for us to use currently, since they have different advantage and also disadvantage across different models.
Let's say for the simple problem of finding point sources, is there something available now to the community for finding point sources?
Yeah, there are a lot. Yeah, the traditional one is the sex tractor that's widely used. That's based on threshold. And there are other methods that's using the wavelet. That's the traditional method. And for the convolutional neural network method, we have using just the simple CNN can do that, just to give the box on the location of point sources. And they can exclude some of the artifacts really good. Yeah, I can show you really quick on
so it works well in nebular regions, and it returns an uncertainty in the derived fluxes that is reliable.
No, this is only doing the source extraction. They are not doing the further analysis. So for example, here they might have, let me see, I have some example here. Yeah, for example, here, even though there are some artifacts, the machine can still exclude all these artifacts in the source extraction, and they can only targeting on the specific galaxies. This is a deep field from maybe Hubble, I guess, and exclude also stars at the foreground. So that's the advantage of machine learning. They can only identify the sources you want them to identify, just exclude all the artifacts or the optical ghost because there are some artifacts from the telescope from here. Yeah.
Okay, so you're saying some packages exist that are off the shelf we can use already.
It's already there, yeah. But you need to probably need to retrain a little bit on your target since we have different requirements or we have different needs for the machine learning model. So we need to always retrain or to try our best to fit our needs or requirement.
Okay, any other questions for Duo?
For the foundational model, it's similar to the large language model, or
Can you repeat the question?
Oh, yeah. So the question was whether the foundation model is similar to the large language model. Since, yeah, for the large language model, it's also called a foundation model. Usually, we just call this large model, or foundation model means we can learn everything we can. So this is in the image domain, and large language model is in the text or the words or sentence domain. That's the text domain. So they are all can call it foundation model because we are learning all we know or all the data we have from our daily life, from our natural science or natural life.
So I think my next question is, if I have a specific idea to look for in these images, may not be point source, may not be galaxy, but something specific. If I have some ideas, that's what I'm looking for. How, like, if there's nobody have established this model before, how hard it is to start a foundation model by itself? Yeah,
the question was when we want to transfer our foundation model to a new task that's never seen before, such as in exoplanet. Yeah.
Identify cosmic layers.
Yeah, yeah. That's never included in the foundation model training. How hard it is to transfer this model to our specific task? The answer is not that hard once you have proper training set. That's a subsample of training set. This is called a fine tune. So we have a foundation model that has already been trained really well on the natural image. So the most of the feature extraction algorithm or the filter or the kernel is being fixed. We only need to tune a little bit on the final or in the intercept of several layers. We can let them to be tuned and let them to be trained on your task, or for example, the cosmic ray or exoplanet identification. Then that will be straightforward to be transferred, since fine-tuning is much time efficient and also labor be efficient. They don't have just the main challenge is you need to provide a clean sample or clean data set for that.
And how much computational resource does it take?
Sam, I'm not sure since I'm running that on the website. So if that can be run on one website, I don't think that's really computationally efficient. So the common GPU can do that, can handle that usually. Since there are some also lightweighted model, especially SAM is based on the vision transformer. And now there is a new vision Mamba, which is much more computational efficient. So that will be even can be running on the laptop with a simple or graphic can do that. So that's since vision Mamba can almost replace the vision transformer, which can be hundreds faster than the traditional ones because they are less computationally expensive. And
so let's say, like, if I want to process 1 terabyte of images, how long does it take to run it on like a laptop?
For example, for the SAM, just when I do that, this image is roughly 512 times 300-ish, and just 1 second, just give you the prediction. Really quick. The prediction is really quick.
1 terabyte of data, that's a lot of 300 times.
Yeah.
Oh, right.
Yeah, but I can do that parallel. Yeah, that can be done parallel. Since the prediction doesn't require you to do training, but you can do a multiple GPU, multiple cluster to do that.
Probably laptop. That's interesting.
Great. Any further questions for Duo before we finish? I want other things there, Virginia, because I have one last. There is some work going on to use machine learning to predict astrochemical models. I know you're not working on that yourself. Well, I don't think you're working on that yourself for Duo, but do you have any thoughts on how how useful that is, really, or what we really learned from that? I'm trying to think of the way to phrase the question here. I mean, we have complicated chemical.
Jonathan, I've talked with a large number of people who have been doing this or have tried to do this. I mean, you can make the chemical networks kind of start to emulate things to kind of speed things up. But the problem is the problem is so nonlinear. You end up basically being dominated by worrying about, is what you're getting actually right? Or you can end up with multiple predictions for, physical parameters that get you the same abundance over time, right? So if you evolve a chemical system for 10 to the 5 years or 10 to the 6 years, you can find parameter spaces where you get similar abundances just at different times. And I think this makes it very difficult to pull out parameters from this type of thing versus, if you just want to emulate something, say, starting with some density, you can kind of emulate it that way. But I think using chemical models as time dependent, in steady state, you might be able to do this because then it's a bit more unique. But yeah, it's
So
a very
why is this different from the other applications that Duo presented? And again, Duo, if you have perspectives on this, but
yeah, since from my knowledge, I know there are two different paths for the chemical model. One is to do the similar to what Brent said, that's similar to analog. That's learning the inference or learning the predict to learn how the input, such as the specific condition, physical condition, or the chemical condition, and then to predict the abundances or the emission between different species. And that's similar to some of the regression or the inference work. And another topic of the chemical network is, I know there are some people using the graph neural network, since that's well learned how different species are connected between each other based on their chemical reaction equation. And then based on this graph neural network, they can do really fast prediction certain species or their abundances. And they can be really dynamic to update your species based on the output from graphic calculation, rather than to do a steady state prediction on the abundances. But building up this graphic neural network, I'm not sure whether some people are doing that, but I'm not sure there are some publication yet to do a dynamic.
Yeah, I feel like there's a bunch of papers that have presented various methods of solving the equations, and they always use very reduced networks. You see in their conclusions, we'll apply for something for a larger network, and for future development, and then you never see it again. And exactly. I've talked with a few of the people who have tried this, and it's because it mostly just fails if you go to very large networks or gas grain networks, because it's just so nonlinear and so sparse. That you end up spending so much time trying to train your thing or trying to get the AI to work that you could have just solved the problem.
Okay, we should wrap up soon, but any last questions?
One very brief last question over here, Jonathan. So about machine learning with RFI, in optical and I guess radio. So are you guys advocating that as a way to get around like Starlink, basically? The issues that
there's already.
Is that like included in maybe like some of the reports that are being discussed?
There's already a series of papers since I've seen that before. Since the Star Trek, they have already developed a pipeline to just extract all these artifacts from the satellite.
And it does a really good job, and it's almost like they were never. Or there's still impacts?
I'm not sure, but they argue they are doing a really good job since from their prediction, compared with the true and the Star Trek contaminated ones, they are really good.
Cool.
Yeah, there are a bunch of people doing that. Since I'm not only astronomy, they're also doing the engineering. People are also doing that.
Right.
Since machine learning is really a big community, and there are a bunch of people doing similar jobs.
Thanks.
Very good, Duo. Well, that's a great overview, and we thank you again for your talk.
Thank you.